Okay, we've been working with the convolution operation, and in the last video we demonstrated how when we use this equation that we can use this to solve the inverse Laplace transform of various expressions. We haven't proven this relationship yet. We would do that in a future video. Also, in the previous videos in our series, we derived the Laplace transform for all of these basic functions. So we're assuming now, as we're working through different examples, that everyone is familiar with these basic Laplace transforms. Now, in this video, we want to consider, suppose we have the inverse Laplace transform, say, of 1 over s squared times s minus 1. How can we solve this one? So again, we write it as a product of two Laplace transforms. And this looks like it would be pretty straightforward. We have 1 over s squared times 1 over s minus 1. And now here's where we had to be familiar with our basic Laplace transforms. 1 over s squared, that corresponds to the function t. Laplace transform of t is 1 over s squared. 1 over s minus 1, that corresponds to, this corresponds to t. That corresponds, 1 over s minus 1 is e to the t. Laplace transform of t is 1 over s squared. The Laplace transform of e to the t is 1 over s minus 1. So this is equal to t, this convolution operation, t, with e to the t. So the inverse Laplace transform of this is equal to this convolution. Now, as you pointed out in the previous videos, this equals this. We can write them in reverse order, and this is the one that we're going to choose to work with, because to write this in integral form, if we do it like that, remember, here's our formula for the convolution operation. F of t is just f of x. E of t is just e to the x. Now, on the right-hand side of the star, g of t becomes g of t minus x. That's t, so this is just t minus x dx. And again, that's just applying the basic formula for the convolution operation. F of t inside of the integral is f of x, e to the t, that's e to the x. On the right-hand side, this is our g of t, and the integral is g of t minus x. Well, g of t is just t, so in here it's t minus x. Now, see, if we had it like this, we put it in integral form. This would be x times e to the t minus x dx. We prefer to work with this integral. So again, when you get to this stage, you write it out the convolution in either order and then try to decide which one gives the simplest integral to evaluate. This might even be easier, but let's go ahead and work with it in this form here. They're both simple integrals. If we had a more complicated problem, one of these integral expressions might be much simpler to evaluate than the other one. So when you get to this stage, write down the convolution in either order, then decide which integral expression is the easiest to evaluate. So let's consider this one. What we have then is that the inverse Laplace transform of 1 over s squared times s minus 1 equals this in an integral form. What we have is, actually let's see now, we want to write this, we had it like this, e to the x times t minus x dx. That's this one that we're working with in integral form. X goes from 0 to x equals t. So finding this Laplace transform is the same as evaluating this integral. And let's see what that gives us. Here this equals t e to the x. Now remember, going back to our operation for the convolution, these are the functions of t. We write them as functions of x inside the integral, and the t now is just taken as a constant. So here we have t times e to the x. T is treated as a constant, so that can come to the outside, like this, dx. X goes from 0 to t minus x e to the x. Dx. Same limits. And of course, this is just e to the x. So this equals t e to the x with its limits minus, and then here we have x e to the x. That's all set up to evaluate. We can do this very simply just by integrating by parts, and when we do that, for this we have, let's write it like this, integrate this by parts, we have x e to the x x goes from 0 to t, and then we have minus the integral e to the x dx, x equals 0 to x equals t. And again, that's just evaluating this using integration by parts, gives us this expression. And remember now, this, which is these two integrals, which comes from this integral, and this integral expression is the inverse Laplace transform of what we have inside of here. So we're going to have to erase all of this to make some room to evaluate this. So let's do that. So our initial problem was finding the inverse Laplace transform of 1 over s squared times s minus 1. And that is equal to t e to the x goes from 0 to t, minus x e to the x goes from 0 to x equals t, and then we had minus the integral e to the x dx. X goes from 0 to x equals t. So evaluating this gives us the inverse Laplace transform of that function there. And why is that true? Because of this equation, which we have yet to prove. We will prove this equation in a future video. But let's see what we have. This equals t e to the x going from 0 to t, and then putting it in here we have minus, here we have x equals t, so we'll have t e to the t minus, when x equals 0, that will be 0. Then we have minus this integral, and that is e to the x going from 0 to t. So this equals, now here we have x will be t, so we have t e to the t minus x is 0, e to the 0 is 1. We have this. Then we have minus t e to the t. Then here we have plus this expression, e to the t minus e to the 0, which is 1. So here is what we have, and let's see. This and this cancel, so we have e to the t minus 1. Remember, our initial problem was finding the inverse Laplace transform of 1 over s squared times s minus 1, and the answer we get is e to the t minus 1. So there it is, and again, it all hinges upon this equation right here. So hopefully we're getting a feel then as to the usefulness of the convolution operation when we need to evaluate various types of inverse Laplace transform expressions. And again, why is this equation true? We will prove that this is true in some future videos. Right now we just want to get used to working with this expression so we understand how to do it, and then hopefully gain appreciation for the usefulness of the convolution function in solving different types of inverse Laplace transform problems. And we'll have some more practice with this in future videos. A reminder, the playlist for all the videos is at the website digital-university.org.